Hello students, welcome to today's session. Today we shall be discussing one important topic of hard and soft acid base concept in one of our playlist of Cakewalk to Inorganic Chemistry. So this particular topic is being asked by many of my students who are preparing this year for IIT Advanced that they find it a bit tricky and they are having some apprehensions in regard to this particular topic. So I thought of placing it for all of you onto the YouTube. So what exactly it is, hard and soft acid base concepts. Let us the video may go little in length because it would be having first theory and then the part 2 and 3 for the application part. So this is quite a lengthy one. So let me give you a little idea what exactly it is being framed which way. So there are different types of acid base theories which are available. We happen to say Arrhenius acid base theory, then Laurie Bronsted, then Lewis acid base. These three are primarily in our syllabus of 11th and 12th curriculum, but you would not find much of this particular theory, hard and soft acid base theory, in our plus one plus two level. So but this theory in itself has some application part in inorganic chemistry as well as in a bit of organic chemistry also. So basically this theory is nothing but an extension of this Lewis theory itself. This theory was proposed by Pearson, who proposed some other things along with what is being proposed by Lewis. It is just an extension of the Lewis acid base theory. And there is another one, flux flood acid base theory. This, if in case you want, I will place it one more video for this. This is not a very tough one, but it is not much used in, it would be used somewhere in metallurgy only. Otherwise it is not much used in most of the topics. So going ahead, let us first understand what exactly do we mean by Lewis acid base theory, just for a fraction of minutes. So what is Lewis acid? Lewis acid is anything which is electron deficient species which is looking for electron, or any species which is seeking electrons. I just say it like this, that any species which is seeking electrons can be said as Lewis acid, because, or in other word, it is an electron pair acceptor, and anything which is looking for electrons must be having some vacant orbitals. These vacant orbitals can be p orbitals. If the species have vacant p orbitals or d orbitals, then it can act as a Lewis acid because it can accept the pair of electrons. Now the matter of the fact is, there are 5 subdivisions in it. There are 5 subheadings in it. What are the type of Lewis acids? There are 5 categories, but here I just be concluding it in 2 subheadings, that I can say it as 2 ways, that one is neutral and another is positively charged. So the neutral one, like BeF2 or BF3, so here the octet is incomplete and they have vacant p orbitals. So these vacant p orbitals can accommodate pair of electrons. So, and similarly, if I go further, these are some of the Lewis acids which would have vacant d orbitals for the accommodation. So these are having vacant d orbitals, so they may accommodate pair of electrons from the Lewis space. And as regard to the positively charged species, these are obviously would want the octet of H positive is incomplete, and this also is a selenium cation, nitronium. So anywhere you would get the positive charge, that can act as Lewis acid. And as a matter of fact, this Lewis acid in our organic chemistry, we tend to say these as to be electrophiles. Electrophiles are the substances or the species which are looking for electrons, or which have a great affinity for the electrons, merely because of the fact that they don't have uh, their octet incomplete or something like that. So moving on, let me hurriedly would tell you what is Lewis base also. Lewis base is anything which is electron rich. It is a electron rich species, or it is a electron pair donor, or it is electron rich. And this can also be tabulated in 2 ways. One, you can say it as neutral Lewis base, neutral, and another one is negatively charged. So as a simple viewpoint here, negatively charged. Simple viewpoint here is that any species which is having a lone pair can act as a source of Lewis base, and whereas any species which would have any negative charge can act as what you call it as Lewis base. And in organic chemistry, we say this Lewis base has to be nucleophile most of the time, and in inorganic chemistry, if I say it, inorganic chemistry, this Lewis base also would be tabulated as or mentioned as ligand. This also is very interesting. And in organic chemistry, we happen to say that Lewis base and nucleophile can be same and different, but that is a very good, interesting paradox there, that what are the when and how a given species would act as nucleophile and would act as a base. Now, as a matter of fact, now let me move further and what exactly is. So I gave you a brief idea about Lewis acid base theory. Now, what is hard and soft acid base principle or theory it is? Basically, it is defining this particular principle would be defining any Lewis acid into two categories. One, you can say it as to be hard acid, and another you can say it as to be soft acid. Similarly, for a Lewis base also, this is being proposed by Pearson. Pearson did the extension of this theory only of Lewis acid and Lewis base, and he tabulated these whatever example I have given. They converted or they said it in terms of hard base and soft base. So going forward, I shall be using this as HA and this as SA, and this would be hard base and this would be soft base. Now, make it a point, what is the thumb rule for this basically? The thumb rule in this theory had been that hard acid would always want to interact or would get stabilized when it combines with hard base. And similarly, soft acid, why is it doing so? We will see in minutes time, would always want to interact with, or it would prefer to get attached with soft base. So this is the basic principle on which this theory runs, that the stability of those particular type of compounds would be high where hard acid combines with hard base or soft acid combines with soft base. For the understanding of this theory, I would advise all of you to just read a chapter of chemical bonding, and in chemical bonding I would want you to, and a bit of periodic table, you should know the basic trends of atomic size. Then you also know the trend of electronegativity. You also should see, I would say, that the topic of Fezan rule, or where you have come across the topic of polarizability or polarization. That particular topic would also assist you to understand this principle in a better way. Now, let us go into the details. What exactly it is, hard acid and soft acid, what are these? Now, I just have marked it this way, that hard acid is anything which would have small size, high charge density or high charge, a species or a cation, any species or cation which would have small size and high charge on it, or greater charge density, or more is the effective nuclear charge on that particular cation, that would be classified under the category of hard acid. On the contrary, soft is the one in which the size is big and the charge density is low, or I would say the size is small here, here it is large, and charge here is high, here it is low. And also you have to understand that the cation for which the valence electrons are tightly held by the nucleus, when the electrons of the any positively charged species are tightly held by the nucleus, then we will say it is not easily polarized. So the polarizability of a cation or a neutral species, when it is low, we will say it is a hard acid. And when the polarizability of a given species as cation or neutral molecule is easy, or here it is the polarizability is low, here the polarizability is high, because the valence electrons are not strongly held from the nucleus. When the electrons are not strongly held from the nucleus, we will say it is easily polarizable. So that particular type of acid would be called as soft acid. So here I am placing some examples, and you have not to get disturbed by so much of examples. I would tell you what are the examples you should focus on. So first let me tell you, so H positive is the hardest, I will say this is the hardest acid. You can say it like this is the most hardest acid, H positive. And then alkali metals, and then alkaline earth metals, all these are positively charged, and these are the species which would have 3 positive charge or 4 positive charge. So in simple words, what you have to remember, lighter transition elements, I may say it like this, lighter transition elements in higher oxidation state would fall under the category of hard acid, as simple as that. Lighter transition elements like scandium, chromium, cobalt, iron in lower oxidation in higher oxidation state +3 or +4, then they tend to behave like a hard acid. On the contrary, soft acids are the one where you would see this copper 1 positive, silver, gold, thallium, mercury, cesium, platinum. So here what you are able to see that all those transition elements which belong to 4D or 5D series, 4D and 5D series with low oxidation state, as simple as that. Transition elements, because here you have to just remember the inference, not have to go into the much of the details of every example, because HSAB is just a qualitative way of defining some properties. It is not a, you are not able to quantify with some way. It is a qualitative approach, nor a quantitative approach. So now what I am saying is that Lewis, soft acids are those, if I say soft acids are those where the cations are of transition elements belonging to 4D or 5D with low oxidation state. And also you should remember that sulfur, selenium, iodine, bromine, because these again are of the p block down the group and with a low oxidation state, they would also get classified into soft acids. Now, another example which you should focus on, which we shall be discussing in more detail in a minute's time, these are some of the neutral examples. This you have to remember as such, these are quite important. Now here, this BF3 versus BH3, this we just be explaining in the application part where I have discussed the topic of symbiosis, how the topic or concept of symbiosis makes a given species hard or soft by placing the ligands in such a way that the ligands tend to do the hardness or softness of the central atom. So that would be clear in that application part. You just go through that video. So BH3 is soft, but BF3 is hard. And similarly, SO3, because the sulfur is in +6 oxidation state, phenol is a hard, carbon dioxide HF, because it is both H and F, H positive and F negative, both belongs to the hard one. And now here you have to remember these are the some of the examples which are borderline cases. As I am again and again suggesting you that it is a qualitative way of defining this, and these are just being said as borderline examples, that they may act as strong as well as base depending upon what type of base it is going to get attached with. Now coming on to the hard and soft base, it is easy. Hard base is again the one which would have high electronegativity. The polarizability is poor. They are not easily polarized because they are tightly held. The electrons are tightly held because of the high electronegativity, and they would have fully filled orbitals, that they don't be having any orbital which would be partially filled. They would be having fully filled orbitals. So that, as a matter of fact, again I may say any species where the charge density is high, that would come under the category of hard base, and that would be possible if the electronegativity is high and effective nuclear charge felt on the valence electrons is more, so they are poorly polarizable. And here the electronegativity is low and polarizability is high, and they would be having partially filled orbitals. And because of these partially filled orbitals, the hold of nucleus on valence electron is not very much, so the electron cloud could easily be polarized by a incoming cation. Now here what the simple trick to play here is that all those would come under the category of hard bases. All those species would come under the category of hard bases where you have the donor atom is nitrogen, Just see, I'm underlining the nitrogen or oxygen. These are the oxygens, carbonate, phosphate, oxalate. When the donor atom is oxygen. According to Pearson, he proposed it, he observed it that way, that whenever the donor atoms are oxygen or nitrogen, they would fall under the category of hard bases, and fluoride and chloride also comes under this. On the contrary, whenever the donor atom is either sulfur or phosphorus, sulfur, just see the sulfur and phosphorus, then this tend to become as a soft what? Soft base. And down the group, if you go for, now these are some of the important examples which I mark it. Cyanide is an important example, iodide, carbanion is a soft, or carbanion, benzene, ethylene, carbon monoxide. These are some of the important examples which you should remember, because these would be used while discussing the application part. Again, you have some borderline cases. Here people ask me borderline cases, and a question could come that how sir is defining which one is hard and which one is soft. Hard and soft basically depends upon the polarizability, as simple as that. If the cation is easily polarized, then it is soft, and anion is easily polarized, it is soft. If it is not that way polarized, or it is having a good charge density on it, and it is not easily get polarized by anion, then the one which is not easily get polarized by anion would be hard cation. If it is easily polarized, then it would be soft cation. So all of these are being observed. This is being observed, that these N3 negative nitrogen. So here is a remark to all of you. This azide ion would fall under the category of borderline. So I said that the hardness or softness of a given species is a qualitative way of identifying the thing. But some of the foreign author books are endorsing the fact that if you know the value of ionization potential and electron affinity for a given species, then hardness can be defined as eta equal to 1/2 the ionization potential minus the electron affinity. So it has been seen this particular viewpoint is being proposed by Millikan, and many of the books, foreign author books, endorses this point that you can evaluate hardness this way. So greater is the difference between these two. So greater is this difference, we would say greater is the hardness of a given chemical species, and lesser is the difference, more would be the softness. So make it a point that it would depend, this quantitative aspect can be taken into consideration only if you know the values of ionization potential and electron affinity of a given chemical species. Now, as regard to the polyatomic molecules, there also you have to, if you want to quantify that also, that whether a given neutral molecule would act as a hard acid or a hard base, and or a soft acid soft base, then for a neutral molecule, with the few examples which we have already taken, here it is related to a fact that the energy difference between HOMO, that is highest occupied molecular orbital of that particular molecule, and LUMO, lowest unoccupied molecular orbital. So many of you people might not be knowing HOMO and LUMO. Basically, if I would give you in a fraction of minutes that if you have a molecular orbital diagram of this type, one is the bonding, another is the anti-bonding, and if say for example this orbital is filled, so we shall be saying this as highest occupied molecular orbital, and this which is vacant one, we call it as lowest unoccupied molecular orbital. So what we are saying is, now here you have, if you want to do the quantification here, you need to know the energy difference here, and this energy difference, if it is greater for a given chemical species or for a neutral molecule, greater is its hardness. So larger the difference between, or large is the energy gap between LUMO and HOMO, greater is the hardness. The hardness would depend upon the energy difference of, so here it come from the topic of molecular orbital theory. So here, to identify this hardness, you need to know the molecular orbital theory. And this energy difference also tells us about the chemical reactivity. This is also a very beautiful thing which you should remember from the MCQ point of view, chemical reactivity increases when the energy of LUMO, lowest unoccupied molecular orbital, decreases and that of HOMO increases. So if this is the LUMO and this is the HOMO, highest occupied molecular orbital. So if this energy goes up and this goes down, so this energy gap, this energy difference decreases. So delta E decreases. If this energy difference decreases, the reactivity increases. So this is very interesting to tell you that soft species react faster because the energy difference between their LUMO HOMO is lesser compared to their counter hard parts. So hard one, the hard acid or hard base would have greater difference, whereas that of soft, they have the energy difference lesser, and because of the fact they react faster. And this also is being endorsed by a point that soft acid base have the ability to form pi bond, and this in a way also endorses the point that they are having a little more reactivity speed. The speed with which they are going to react would be faster as compared to the hard ones. So that is what you have to remember. So let me consolidate. One more thing I should place it here, that if you go for a given hard base or a soft base, if you go to this side, hardness increases. This is a very simple viewpoint. And if you go to this side, softness increases. So make it a point, it only depends on the fact that nitrogen, oxygen, fluorine are hard bases and these are soft one. And lastly, let me consolidate what we have learned is that a from an organic standpoint of view, that hard nucleophile prefers hard electrophile and soft nucleophile prefers. This is the thumb rule of this HSAB. And similarly, hard acid prefers to bind with, here it should be written as bind with hard base, and soft acid would like to bind with soft base. So this conclude with the theory, and in the upcoming session of this part 2 and 3 would be the application part. So don't forget to see into that video, because that would be the application part, that whatever we have learned in this theory, how these are to be applied on to the problem solving. Thanks a lot. Have a nice day. Stay safe and take good care of yourself.